Okay. So good evening, everyone. Welcome to the eighth live session of mine for the course Design of Reinforced Concrete Structure offered by NPTEL. I am Harshit Agrawal, PMRF Research Scholar from IIT Bombay, and I will be conducting weekly live session for all 12 weeks of this course. So just to start with, what is this session all about? So these are weekly interactive sessions that will happen every Tuesday from 6 p.m. to 8 p.m. till the course run. How do we interact? By answering the questions that I will ask in the chat box, by posting your questions or queries in the chat box, or by raising hand, unmuting, and asking your queries. Apart from the discussion in class, you can always use the discussion forum of the course that is there in the NPTEL site, and you can raise your questions there also, the answer to which will be given there only or in the next live session by any one of the TA. And through this course, you will be able to answer the graded assignments easily, and you will it will help you to develop further understanding about complex topics holistically. So I hope everyone are clear what the session is about. So, in today's session, we will first have a look at what we discussed in the last live session that was for week 7 of this course. Just a quick glance. Then we'll discuss the week 8 content, wherein today we will continue our discussion on design of RC columns. So today we'll first get started with discussion on eccentrically loaded short column, wherein we will understand the PM curve interaction and how it is considered while designing using SP16 handbook. Then we'll see a numerical on uniaxially loaded short column. After this, we'll discuss about biaxial loaded short column, how it is designed and the numerical on it. And finally, we will discuss slender columns, how the additional moments due to slenderness is calculated, and then we will end our session by concluding the week's discussion. So, in the last live session of mine, we talked about design of RC columns. We first looked at what are columns. So, simply saying, columns are vertical compression members which provide elevation to an RC structure. So, you can see in these images, these are the columns which are elevating our structure. Okay, they provide elevation to our structure. Then we say an element is column if the length of the column is more than three times the least lateral dimension. Okay. Then we saw some important design parameters of reinforced concrete column. What are those? Dimensions can be either square or rectangular, circular. That is important to be chosen properly during the design. Then there is cover. So cover is generally taken more than 40 mm. That also becomes important when we are calculating effective depth and reinforcement spacing. Third is mean reinforcement, or we can say longitudinal one, which resists the compression load along with the concrete and also resists the bending. And finally, there are transfer reinforcement, or which is also known as tie bars. Okay. So as the name suggests, it is used to tie the main reinforcement and keep them intact in the position. Then we classified our column. So we understood each parameter, how it is important in terms of designing. Then we classified our columns based on first dimension. So that can be a short column and there can be a slender column. How? By calculating the ratio of effective width to the lateral dimension, which is also known as slenderness ratio. If the slenderness ratio is less than 12, then we say it is a short column, else it's a slender column. Then we classified column based on loading. So there are two kinds of columns: axially loaded column and eccentrically loaded columns. What can and Going deep into this, we talked about design of axially loaded short columns, what conditions need to be checked and how to design. And apart, we looked at one numerical also for designing the axially loaded column. And finally, we initiated a bit of discussion on eccentrically loaded column also, and just caught a glance of what SP16 PM curves are. Okay, so I hope the last week content was clear to everyone. Now, one question was asked last week regarding the choice of effective length, like how different end conditions are practically possible. Like we say in columns, there are fixed support, hinge support, roller support, but practically in a building, we always see fixed support, where we see other kinds of support. Okay, so just to have a small discussion on that, we have three kinds of support: fixed, hinged, and roller support. Hinge support means it is able to rotate about the support, but it won't move. Roller means it can move, and fixed means it can't do anything. Okay, so where we find hinge support at beam column connections, when rotation, when we need to allow rotation due to bending, while it can just resist the vertical load. So at beam column connection, there are generally hinge supports that are provided. Okay, these kind of supports, what they can allow, they can accommodate the rotation due to sway or other movements, and they will create less stress on the structure, and that's why they are provided in the connection part. Second kind of supports are roller supports. So these supports are used when expansion joints of bridge structure. So what they allow the bridge deck to move longitudinally due to temperature change and other factors which can change, which can cause the expansion while providing the vertical support. So this is how they are able to adjust that expansion nature of temperature due to environment into account in bridges. Okay, and in long RC structures also, like elevated walkways and everywhere, you find roller support to accommodate those thermal expansion and contraction. So mainly when there is a cases of thermal expansion and contraction, which when there are scenes where contraction and expansion can be critical, we provide roller support. And finally, there are fixed supports. So in building foundation, stability and rigidity are very important. So in these cases, fixed supports are provided to resist both horizontal and vertical movement. Similarly, in retaining wall also, we need stability and rigidity, so that's why fixed support are provided. And in high rise building also, core walls, shear walls, they are all provided with fixed support. Why? Because we need to resist the lateral loads like wind and seismic forces. And in multi-story building also, columns are fixed at their bases to provide stability and prevent any lateral sway. So mainly in case of buildings, RC buildings, we go for fixed support where we don't need any kind of movement, or where movement due to wind and seismic can be a very critical factor, then we need to go for fixed support. Okay, so these are three different kinds of support. Now, understanding the application where the support are used, you can accordingly plan the design. So like if a column is given and it is used at some location, and if it is not given what kind of support is provided there, you can make your own assumptions. Okay, so moving ahead, so let's start a discussion on the eccentrically loaded columns. So what are these? When axial load is acting on the column is not along the central axis, then we say it is an eccentrically loaded column. So last week we saw, suppose this is my top view of a column and these are my central axis. So if my load is acting just at the center, then we say axially loaded column. But suppose if my load is acting here or here somewhere, it is not at the center, then we say it is a eccentrically loaded column. Okay. So in this, apart from axial load acting on the column, there can be some movement also that is generated due to eccentricity, which needs to be taken care of. So to take care of both load P and moment mu, we use SP16 chart, wherein knowing some basic design parameters, we can calculate the percentage steel required. So if we know the grade of steel, effective depth to total depth ratio, and the values of FCK and dimensions of the columns, we can calculate different factors, and using those factors, we can calculate the percentage steel that is required for us to provide, so that that column can resist both load and moment. But and this is one of the example of the chart that is present in SP16, that we will also use today when we will solve the numerical. But how this chart came into existence, that is important for us to know. Okay, so if we see a uniaxially loaded short column, there is a load P that is acting on the column, and there can be movement along X or Y along with the axial load P. So there will be compression in the column, and suppose my movement is along this axis, y axis, then there can be bending also that can be generated in these outermost fiber. Okay, so just like what we saw in the beam design, uh, due to this, this fibers can bend like this, and thus we also need to take care of movement. Okay, so now, some of you might be confused, like this is not a slender column. Then why we are talking about bending here and all? So you should know the difference between two terms, bending and buckling. So right now, what we are talking is bending, and there is one more thing that we will talk on later, that is buckling. So bending is due to transfer load or some external movement that is acting directly or generated due to eccentricity. But buckling is something that is that is a bending that is generated due to axial load. So if you see, if this is my column, okay, and this is the load that is acting, and there is a eccentricity E, then due to this eccentricity E, there can be some bending moment that is generated on the column. Okay, so this is known as bending. Okay, and that can occur in both short column and long column. But when I have a long column, what happens? I have a load P. Suppose this is an axially loaded column. So what will happen? Due to this load, there can be some deformation in the column, and this deformation will give rise to some eccentricity, and this eccentricity can generate buckling, can generate moment, and that is known as buckling. Okay, so both are the different thing. There here, due to the deflection in the column, bending is occurring, which is known as buckling, and it is generated due to axial load. And here, bending is there due to externally applied moment or externally acting moment on the column. Okay, for now, just keep it simple. We will have this discussion later on also for much clarity. So we'll go deep into this again. Now, when we have both movement and load, uh, acting, now these moment and load are acting along different directions. So suppose I have a column like this, my load is acting around this direction along the axis, while my moment will be acting perpendicular to the axis. So we need to have some interaction diagram between them, and that's how pm curve came, wherein, so this is how PM curve look like. So wherein my y-axis is representing my load, axial load, and my x-axis is representing my moment. So if I am on a y-axis, it is like an purely axially loaded column, and if I am on a x-axis, it is purely in the moment. So when there is both moment and load, so this is how my interaction diagram comes up to be. Okay, so just to normalize these curves for any grade of concrete and any dimension of concrete, what IS code did, they divided the axial load by a factor PU by FCK BD, and divided the moment by a factor PU by FCK BD square. So these becomes a dimensionless quantity, and if we know these values and our grade of steel that we need to provide, and the effective depth that is there, we can calculate the area of steel by just calculating the interaction of these 2 points and then checking which curve it belongs to. Okay, so the same thing is written here. We have fixed parameter, concrete grade, ultimate load, ultimate moment, and dimension. Using these, we can calculate the x and y axis parameters. Based on these parameters and knowing the other dependable parameters like steel grade and the ratio of effective cover to depth of section, we can calculate the percentage of steel that is needed to be provided to resist both load and moment. Okay, so I hope this how this interaction curve came into existence, why we are dividing PU by FCKBD and MU by FCKBD square, and how to design is clear to everyone. Now we will look at one numerical regarding this, so that application point of view is also clear to everyone. Okay, so this is the numerical. What this numerical says: design a column subjected to a design load of 1000 kilonewton and a design bending moment of 100 kilonewton meter. Unsupported length of the column is 4 meter with support rigidly fixed and effectively held in position. Consider M20 and FE500 grade of concrete and steel respectively. Design the transfer reinforcement also. So I will wait for 5 minutes, and I will give you a chance to think how to solve this question and how to proceed ahead, and then I will solve. Okay, so let's see the solution now. We will proceed in a very step-by-step manner so that everyone understands like how moment is becomes important. Okay, so first we'll design this question like it is an axially loaded short column only, and then we'll see with moment what differences occur. Okay, so what are the given things? So we have given design axial load, which is Pu is equal to 1000 kilonewton. Mu is given to us 100 kilonewton meter. Okay. Unsupported length L naught is given to us as 4 meter. FCK is given as 20 and Fy is given as 500 MPa. Okay, so these are the data that is given to us. Now it is written in the question the supports are rigidly fixed and effectively held in position. So if we refer to table 28 of IS 456, we'll get that L effective is equal to K times L naught, and the K value for this condition is 0.65. Okay, so 0.65 times L naught, which is 4. So we will get our L effective as 2.6 meter. Okay. Now it is not given to us anywhere in the question that it is a short column or a long column. Okay. So let's assume the column to be a short column. Okay. I'm assuming. We will later on verify if this assumption is true or not. And let's assume percentage of steel equal to 2% of gross area. Okay. So if my gross area is denoted by AG, so my AS is nothing but 0.02 times AG, and my AC is nothing but AG minus ASC, so it will be 0.98 times AG. Okay, so these value I know. Okay, and right now I have made an assumption that the column is a short column. So I'm marking it as in red since it is yet to be verified. Okay, now let's solve it. So I will just append at the top what all things we know and what all things we have calculated till now, so that in the end the top line can show you all the results. Okay. Okay, so this is points that we know right now. Now we know as per IS code, IS clause 39.3, PU is nothing but zero point 0.4 FCK AC plus 0.67 Fy AC. Right now, I am not taking bending into account. I am just talking about pure actually loaded column. So here PU is nothing but 1000 kilonewton, so 1000 into 1000, which is equal to zero point 0.4 times 20 times 0.98 times Ag plus 0.67 times 500 times 0.02 times Ag. Okay, so we have one variable gross area. So gross area on solving, it will come out to be 1000 into 1000 divided by 14.54. Now this right hand side calculation. So it will come out to be around 68775.8 millimeter square. Okay. Now we know the gross area, so we need to choose the dimension of the column. What kind of column that we need to provide? So I am assuming square column. Okay. So my AG will be nothing but B square, which is equal to 68775.8 mm square. So from this, if I calculate my lateral dimension of the column, it will come out to be square root of AG, and it will come out to be 262.3 mm. So I will take it as roughly as 300 mm. Okay, since we can't provide a column of such an accurate b value, we need to have a whole number or a round up value. So I'm going with 300 mm. So my dimensions of the column are 300 mm cross 300 mm. Now we need to check the slenderness ratio. Initially, we assume that it is a short column. Now, actually, is it a shorter column or not? That we need to check. So, slenderness ratio is nothing but L effective by lateral dimensions. It will come out to be 2.6 meter to 2600 divided by 300, which is nothing but equal to 8.666, which is less than 12. So, this proves my column is a short column, and the assumption was valid. Okay, so this is our check on short column. Now, how to take moment into account? Okay, so for that, let's first calculate the eccentricity. Okay, what is the eccentricity? E minimum. Okay, so how it is given? It is nothing but L naught by 500 plus D by 30, that should be greater than or equal to 20. That is what IS code says. So what we are getting, L naught by 500. So 4000 by 500 plus 300 by 30. So this value will come out to be 18 mm, which is not greater than 20 mm. So my E minimum will be 20 mm. Now, due to this eccentricity, what moment will be generated? So moment due to this eccentricity is equal to nothing but Pu times E minimum, which is equal to 1000 into 20. So this is in kilonewton millimeter. I will convert it into kilonewton meter. So divided by 1000 again. So it will be 1000 kilonewton meter. Okay. So this is the moment that has been generated due to this eccentricity. If I assume my load is acting at a distance of 20 mm, so this much movement will be generated. But my design moment that is given to us in the question is much greater than this moment. So we'll consider the design moment only, okay, for the for designing the column. Okay, so what all data now I have? Extra data. So we know dimension 300 mm cross 300 mm, and we know the short column. Okay, so this is an additional data that we got. Okay, now we need to consider moment also. My design moment is, okay, so design moment mu is 100 kilonewton meter. Okay, so let's assume reinforcement is equally distributed along all four sides. Okay, generally it should not be done since it is an uniaxial column, so our reinforcement distribution to should be mostly away from the axis along which the moment is acting. But for now, let's assume my moment is unit reinforcement is equally distributed on all four sides, and I am assuming a clear cover of 40 mm. Okay, and diameter of bar, that also I need to assume because I need to calculate the effective cover. So diameter of main rebar, that is mean reinforcement. So let's take it as 20 mm. Okay, so my effective cover will be 40 plus 20 by 2, that is 10. So my effective curve will be 50 mm. And I know my D value is 300 mm. Okay, so my D dash by D comes out to be 50 divided by 300, which is equal to 0.16. Now I will round up it to nearest multiple of 5 because in SP16 code all the values are like 0.05, 0.15, 0.2 like this. So I will assume it as 0.15. Okay, I am rounding up to a nearest value. Now we know the d dash by d, we know fy. So what all other things that we need to calculate? So right now, if we see in this diagram that we saw flow chart, we know steel grade and we know the ratio. We also need to calculate this two values so that we can refer to an SP code. Okay, so just calculating those design value. So PU by FCK BD, it will be nothing but 1000 into 1000 divided by 20 into 300 into 300. Okay, so this will come out to be, just round up to two decimal places, it will come out to be 0.55, and mu by fck bd square, it will come out to be 100 into 10 to the power 6, okay, kilonewton meter, divided by 20 into 300 into 300 into 300. So this will come out to be 0.18. Now I know both PU by FCK BD, MU by FCK BD square. So I need to refer to an SP code now. So if we see, where is the code? Just wait a second. I need to check where the code is. So this is the SP16 code. Now we know by our D dash by D is 0.15 and Fy is 500. So referring to the chart, and we assume that our reinforcement is distributed equally along all four sides. Okay, so we need to go for that chart. Okay, so these are reinforcement equally distributed along all four sides. So here going to Fy 500 and d dash by d as 0.15. So this is the chart. So chart 49, reinforcement distributed equally along all four sides. Fy is 500 and d dash by d is 0.15. So in this chart, let me take a pen. Okay. So my PU by FCK BD value was 0.55. So somewhere here. Okay. And my MU by FCK BD square value was 0.18. So maybe somewhere here. Okay. So my ratio will come out to be very close to zero point 0.2. Okay. Somewhere near here. Okay. If you will more accurately see, it will be like very close to this point. Here, if I will go from middle. Okay. So somewhere just in between, I can say less than, a little less than zero point 0.2. Okay, so I will assume that P by FCK value, it will come out to be say point between zero point 0.2 and 0.19 and 0.2. So let's take a midpoint 0.195. So I know the FCK, it is 20, so my P will be 0.195 into times 20, which is 3.9%. Okay, so this is the percentage of steel that we need to provide. Initially, what we got from just axially loaded, if we consider, we assume 2%. Now we are getting 3.9%. So this shows that initially, if you were provided 2% steel, it would be able to resist the axial load, but the moment it won't be able to resist. So we need to provide a little higher percentage of steel. Just to round it up, let's say we are providing 4%. Okay, just to be on the safer side. Okay, so if we are providing 4% steel, so my ASP will come out to be 4% of gross area. So 0.04 times 300 into 300, which is nothing but 3600 mm square. And since I considered 20 dia bars, so my number of rebars will come out to be AC upon total area of sheet. Okay, so that will come out to be roughly like 11.5. It will come out, so I will convert it into 12 numbers. So we need to provide 12 numbers of rebars equally distributed along all four sides. Okay, so if we try to sketch this, how this will be done. So suppose this is my top view of the column, and I need to provide 12 number of reinforcement. So here will be one on the edge. First we will provide all four on the edge. So four are done like this. Then here I need to accommodate 1, 2, 3, 4, 5, 6, 7. Two more on each side. Okay. So equally spacing we can keep, and we can design two rebars more. So like this, the rebars will come. Okay, equally distributed along all the four sides. So these are 12 number of rebars. The spacing you can calculate, and you always need to check whether the spacing is minimum or not, so that the aggregate can pass. So if we assume a aggregate size of 20 that we are using maximum course aggregate size, so this spacing should be at least more than 25 or 30 So my side is 300 cover on both the side is like 50 so my effective distance between these and this end is 200 so what gap I will get? 200 minus 20 minus 20. Okay, so I have 260 divided by 4. So there will be sufficient spacing between the rebars. Okay, so this is true. So always after designing the reinforcement, you need to check with the spacing also. It should be above minimum value. So right now you will get an above minimum value of spacing. So it is okay for the design. Okay, so this is how we considered both moment and load into action. Now there was one more part in the question. What that part was to design for reinforcement. So lateral reinforcement design. How it is done? That is very simple. So diameter of tie bars we choose as uh, more than one fourth of the longitudinal rebar. So my longitudinal is at 20 or 6 So I will consider 6 tie bars. Okay. And spacing. So for spacing or pitch, I have three criteria. It should be at least 300 or 16 times the diameter of longitudinal rebar. So 16 into 20, 320 or lateral dimension of the column, which is 300 So my spacing will be 300 So I need to provide lateral ties all along this. So you can provide either along this side and this side also, or single along all the sides, and it should be 6 in diameter, and it should be at a spacing of 300 center to center. Okay, so I hope this thing is clear to everyone. Okay, just to show you what I was saying about that lateral tie bars. So you can provide either like this one complete, or you can provide with this one complete, one like this also, and one like this also. Okay, so these three kinds of, so this will run, then 6 meter above that, 300 above that, one lateral tie like this, 300 above that, one lateral tie like this, then again this one lateral tie. Okay, so this is how you can also provide the reinforcement detail. Okay, I hope this question is clear to everyone. Okay, any doubt in the solution? Okay, so if there are no doubts, we will proceed ahead. Now, the second part of our discussion is design of biaxial loaded column, wherein there is moment along both x and y axis along with the load. So now when we talk about y biaxially loaded column, what is happening? There is bending here also due to my, and there is bending here also and here also due to mx. Okay, so how the interaction diagram will look like? The interaction diagram will now become 3D. So suppose this is my load axis. This is due to only bending along y as x and due to bending along y. And if both are coming, this will be my resultant interaction diagram. So you can see it is now a 3D diagram. So how to consider all three, the how to design for this. So what is code says, as per clause 39.6, such member may be designed by using the following equation: mux upon mux1 to the power alpha n plus muy upon muy1 to the power alpha n should be less than or equal to 1. Now what are these mu and mux1 and everything? So mux and muy are my moments along x and y axis due to design load that will be given to us in the question, or that we can calculate using the eccentricity along x and y. Okay, similarly what we did in the previous question. And my mux1 and muy1 are the maximum axial uniaxial moment capacity for an axial load pu for bending along x and y. How we will get these two values? By the interaction curves. Okay, so this is something that will be given to us in the question, and this is something that we can calculate from the interaction diagram. And how we get this value alpha n? By using the ratio of pu upon pux. So pux is nothing but my ultimate load. And how it is given? It is given by this formula given in the IS code. So if my ratio is less than or equal to 2, I say my alpha n value is 1. Greater than or equal to it, my alpha n value is 2. And in between zero point 0.2 to zero point 0.8, I need to interpolate. Okay, so this will be something like this, and this. So this is here it is 1, here it is 2 for less than or equal to zero point 0.2, greater than or equal to zero point 0.8. And in between, I will just apply linear interpolation to get the value of alpha n. So it will be between 1 and 2 only, of course. Okay, now just to understand this thing simply, how what is the procedure of design of biaxially loaded column? So we will be given pu, mux, muy, fy and fck. Okay, now based on these values, we need to first assume a suitable dimension of the column, okay, and a suitable cover d dash, and we need to assume percentage of steel p and compute p by fck. Now if I have this value, if I know pu, fck, bd, so what I can do, I can calculate those parameters that we need in the pm interaction curve, and I can calculate mux1 and muy1 from the pm curve. Okay, now knowing mux1 and muy1 and mux and muy, I can check for safety as per the clause that we discussed in the last slide. If that value is less than or equal to 1, I can say it is passed. If that value is not less than or equal to 1, then we need to again assume some dimension and percentage of steel and again do the calculation. Okay, and if it is passed, then we can design the reinforcement. So we know the percentage of steel P and we know the diameter D. Okay, that is something that we assumed initially only. So knowing both the things, we can design the reinforcement for size, number and distribution. Okay, it will be looking a little confusing, but when we will solve the numerical, it will be very clear to everyone. Okay, so let's see one numerical on this. Just remember this flow. Okay, so this is the second numerical. Design a short column subjected to a baxial bending with following data: size of column 300 cross 600 mm, length is 3 meter, factored load 1200 kilonewton, factored moment acting parallel to the larger dimension, and shorter dimension it is given 150 kilonewton meter and 90 kilonewton meter. So this is something mux and muy which is given to us. Okay, and M20 grade concrete we need to use, and Fe415 grade steel we need to use. So I will wait for 5 minutes for you guys to try, and then we will solve. Okay, so let's see the solution now. So what all things are given to us in the question? So text box. We know B is equal to 300 mm, D is equal to 600 mm. So these are the dimension. L naught, it is given to us as 3 meter. Okay, factored moment along larger side. So suppose this is my larger side. So along x-axis, my moment MUX is nothing but 150 kilonewton meter. MUY is nothing but 90 kilonewton meter. PU is given to us 1200 kilonewton. Okay, so these all things are given to us. Okay, now since L naught and other things are given, I can calculate minimum eccentricity first. So minimum eccentricity is nothing but L naught by 500 plus D by 30. Okay, this is along x direction. Okay, so this value will come out to be 3000 by 500 plus 600 by 30, so it will come out to be 26 mm along x direction. And if I see along y direction, it will be L naught by 500 plus b by 30, so it will come out to be 16 mm. Okay, along y direction. Okay, so my minimum eccentricity E minimum here will be 26 mm only, and here my E minimum will be 20 mm. Okay, now I know the factored load, so I can calculate the moment due to eccentricity. So it is nothing but PU times E minimum. So it will come out to be along x direction, it will be 1200 times 20 divided by 1000, because we need to convert mm into meter also. So 1200 into 20 divided by 1000, so it will be 24 kilonewton meter moment due to this eccentricity, and along this direction it will be 1200 into 26 divided by 100, so 31.2 kilonewton meter. Now both of these values are less than the design moment that is given to us. Okay, so we can just design for the moment that is given to us, and we don't need to worry about the moment that is generated due to this eccentricity. Okay, so this is first check that we always need to do. So the design moment we can see is greater than the moment imposed due to the eccentricity, and thus we our moments will be our design moments will be 150 kilonewton meter and 90 kilonewton meter. Okay, now let's see the next part. So we have confirmed what moment we need to design for. Okay, now I won't go in the same manner that I did in the last question, like with PU first calculating and then checking for MU, because now we know the importance of MU. So directly I'm skipping that part and moving to the second part. So let's assume reinforcement is equally provided on all four sides, and CC is equal to 40 mm. And since there is larger moment acting this time, I will assume diameter of rebar equal to 25 mm. Why I am doing this? Why not 20 mm? Because if you will go with 20 mm, what you will encounter, there will be more number of rebars that you will need. And more the number of rebars, the spacing can be an issue later on. We saw one question in the NPTEL session also where they went with the lower diameter of rebar, and in the end they need to redesign with a higher diameter of rebar because the spacing was becoming an issue. So just to avoid that issue, I'm assuming a larger diameter of rebar from the start only. So my effective depth d dash will be 40 plus d by 2, so 40 plus 12.5, so it will be 52.5. Okay, so my d dash by d. Okay, so now uh, d dash by no. Okay, so one more thing, let's assume reinforcement percent that we are providing is 1.5%. We saw in our design chart, okay, what all things we need to start assuming with. See this chart. There's a assume suitable B and D that was provided to us in the question. We have assumed D dash, and we have assumed a suitable percentage of reinforcement so that we can calculate P by FCK. Okay, so I have assumed 1.5% steel. Suppose I am assuming. So my P by FCK, it will become 1.5 divided by 20, so nothing but 0.08. Okay, so this is the P by FCK that I am operating with. Okay, now along x direction. Okay, if I talk along x direction, my d dash by d will be equal to 52.5 divided by 600, so it will be 0.087. I need to square round it up to closest multiple of 5, so I will take zero point 0.1. My PU by FCK DD, it will be 1200 into 1000 divided by 20 into 30, 300 into 600, so this value will come out to be 0.33. Okay, now knowing these two values, again I will need to refer to SP16 chart. Okay, so right now my D dash by D is zero point 0.1 and my Fy is what F5 we are operating with, FE415. Okay, and reinforcement is equally distributed along all the directions. So I will just go behind. Okay, so this is the chart. F5 415 reinforcement distributed equally along four sides, d dash by d zero point 0.1. So right now what I have, okay, my P by FCK is zero point 0.8. So I need to look at this curve. Okay, I'm just highlighting for you. And my PU by FCKBD, it came out to be 0.33. So somewhere here. Okay, so if I draw a horizontal line from here till this line, and then I draw a vertical line here downstairs. So what you will get, this value will be in between zero point 0.1 and 0.15 somewhere. Okay, so just for safety, what we can do, we can assume 0.15. Okay, generally we should not do like this, but for us on to be on the safer side, let's assume we are providing 0.15. Okay, it should be 0.125 or zero point 0.13, but on safe, just to be on the safer side, I am assuming this value I am getting from SC16 is 0.15. So if this value is 0.15, my MUX1 I can calculate. So it is 0.15 into 20 into 300 into 600 into 600. So it will come out to be 324 kilonewton meter. Okay, so this is my MUX1. Now the same thing I need to repeat along x direction also. Okay, so similarly I will just copy this so that you know that this is in repetition. Okay, just removing this part above. Okay, we provided d dash as 52.5 mm and d dash by d ratio was zero point 0.1 that we took. Okay, Okay, so along y direction what changes will occur? So my b dash by b it will become. Okay, so b is nothing but 300. So this value now will become double. So 0.175. So I will assume as zero point 0.2. Okay, I am appending the older text so that you know the difference. My PU by FCKBD it will remain the same. So now what my MU Y1, what this value will be? So again, referring to the chart, d dash by d is zero point 0.2 now. So this is zero point 0.2. Okay, my PU by FCK is 0.33 somewhere here, and this curve is somewhere here. Okay, here we will come. Okay, so if you will see here, and if we go here, it will come out to be just close to zero point 0.1. Okay, near zero point 0.1. Okay, so let's assume it is as zero point 0.1 only. So if it is zero point 0.1, then my value will come out to be zero point 0.1 times 200 times 20 times 30 times. This will be 600 times 300 into 300 now. So it is close to 120 kilonewton meter. Okay, and check the calculation once. So your MUY1 will be close to 120 kilonewton meter. Okay, 118 or 108. Sorry. Okay, 108 kilonewton meter it will come out to be. Okay, so we know MUX1 and MUY1. Okay, both value we know. Now we need to calculate alpha n also. So for alpha n, we need to refer to that chart. Okay, so I'm just deleting the unwanted things now. So first I need to calculate PUZ. Okay, what it is? 0.45 FCK AC plus 0.75 FY ASC. So it is AC is nothing but AG minus ASC. Okay, so 1.5% we assume. So if you will substitute all the values, you will get PUZ as 2420 kilonewton meter. Okay, just substitute the values, you will get this. So PU divided by PUZ, it is nothing but 1200 divided by 2420. So it is very close to zero point 0.5. Okay, 0.49 we can say. So now we can calculate alpha n by interpolation. Since my PU ratio is between zero point 0.2 and 0.28, you can calculate alpha n by interpolation. So I'm just directly writing what value will get so that we can quickly see the result. So your alpha n will come out to be, since it is almost in between, so it will come out to be 1.1, 1.5. So since this value zero point 0.5 is in between zero point 0.2 and zero point 0.8, we can directly write alpha n as 1.5. It will be roughly 1.48, 1.49. I am assuming as 1.5 just for simplicity. So now knowing this value, what we can do, we can use this equation. Okay, I will just copy the equation from here. So my mu x1 now, it is nothing but 150, and this value I got as 324. Alpha n is 1.5. My mu y1 is 90. This value I got as 108, and alpha n is 1.5. Okay, so if you will calculate this, it will come out to be, just do the calculation once. Okay, so both the values are less than 1 to the power 1.5. I will just let give me 2 minutes to do the calculation. Okay, so this will come out to be very close to 1.98 or something, I guess. Okay, so if it comes like this, what we can do, we can assume that the percentage of steel that we have provided is safe for design. Suppose your value comes out to be 0.1.08 or something, then what you need to do, you need to append this percentage. Take this percentage as 2, again calculate P by FCK, again calculate both the moment, and again do the calculation. Okay, so right now I am assuming, suppose this is true. Okay, so if this is true, what we need to do, our design is safe with 1.5% steel, and if it happens like this, we can calculate number of 25 mm rebars needed. So how we can do? So AC is nothing but 1.5 point 1.0.15 times BD. So that I know, I can calculate. This will come out to be 2700 millimeter square. So my number will come out to be area of one rebar upon total area. So it will come out to be 5.5 something. But since we need to equally distribute rebar on all the four sides, let's assume I am providing 8 number of rebars. What this will also do, if I'm providing 8 number of rebar, my ASC will also become greater than 1.5. So this value which was very close to 1, it will reduce now. This value will come out to say zero point 0.8 or 0.75, and my design will become safer on to be on the safer side. Okay. Right now the design would be optimum, but just to be on the safer side, I am providing more number of rebars. So now we will provide 8 rebars. So just like in the last question, so two, four on the sides and four in the middle that we can provide and then design for. So I won't repeat the transverse reinforcement design here because it is very simple to do. So this is how we design for biaxially loaded columns. I hope everyone are clear with the solution. Okay, if there is no doubt, we'll proceed ahead. Okay, so just remember, you need to choose a percentage of steel, then you need to check and you need to provide the number of reinforcement. Okay, now moving ahead to the last part of the discussion. So this was all that we wanted to discuss about design of short column. So in the last week we saw axially loaded short column, and today we saw uniaxially loaded short column and biaxial loaded short column. So in uniaxial we saw how we first assume percentage of steel, and then we calculate how we first get percentage of steel required for axially loaded column, and then using PN curve we see how that percentage of steel was not enough and we needed to provide additional, and we provided that. And in biaxially loaded column, what we saw, we initially assume a percentage of steel and we calculate the ultimate movement along x and y, and we check whether that percentage of steel is enough or not. If not, we will increase the percentage of steel, again do the calculation, again perform the check. Okay, so I hope everyone are clear with that part. Now we will talk about slender columns. Okay, so if we go by technical definition as per IS 456, so what code says, when the ratio of effective length of the column to the lateral dimension is greater than or equal to 10, we say it is a column is a slender column. Okay. Uh, Now, why this ratio is such a criteria? Okay, why we are taking as 12 or something, and why this ratio, how this ratio comes into picture? Because above a certain length of column, what will happen? Buckling will start coming into picture, which is nothing but moment generated due to the axial load that we discussed earlier on. Okay, so if you see in the image, when we have short column and we have some load acting on the top, then there is not much bending in the column that is happening. So eccentricity due to this bending that is occurring due to the axial load is very small or zero. So there is no additional moment that is coming here. Okay. But when we talk about long column and there is some axial load acting on the long column or a slender column, what happens? The column also bends. Okay. Now, when the column bends, there is some eccentricity that is there in the column due to bending. And since there is some load and there is some eccentricity along, like if you see this point, for this point, load is acting here, and this is the eccentricity for that point. So, due to this eccentricity internally generated due to the bending of column, there is movement along due to the axial load, and this movement that is generated due to the axial load due to the internal eccentricity is known as buckling, and this becomes an issue in slender column that we also need to take into account. So in slender column we can have two cases: axially loaded central column where moment is due to this eccentricity, and eccentrically loaded short slender column where moment is due to both design load and external moment acting. Okay, and the additional moment generated due to the eccentricity, internal eccentricity. Okay, so just don't be confused with the external and the internal eccentricity. Here the load is at the center, still there is some eccentricity, and there is one case where load is not at the center, which is generating some eccentricity, and there is some eccentricity internally due to the bending of the column. Okay, so there are two kinds of eccentricity when we talk about cylinder column. Okay, now how this additional movement is calculated? It is calculated using clause 39.7 of IS 456. So according to this clause, additional moment due to axial load in a slender column can be obtained as MAX and MAY is nothing but PU times D upon 2000 times LEX by D to the 2 square. Okay, this B is the lateral dimension. B and D are the lateral dimension along that direction. Okay, so this is how we calculate the eccentricity. The additional moment is generated to this generated due to the eccentricity. Okay, now the most important thing we all know here is the calculation of effective length, because rather all things will be known to us or given to us in the question, but effective length is generally not given to us. It We have given the unsupported length and the end conditions. So how we calculate effective length? Using table 28 of IS 456. But in table 28 also, if you see, there are some cases, like there are these cases where directly the effective length value is given as 0.15, 0.5, 0.7, or directly just L. But there are also some cases where it is given that it is KL and K is between 0.5 to 1, not a specific value that is given to us. We saw one numerical like this also last week, where we just commented whether the value is less than or 10, and we were not able to obtain the exact value of effective length because of the code limitation. So in such cases, how to obtain the value of K? So in such cases, we go with the calculation of rigidity along the column. So suppose this is my long column that I need to design. This is column above it, column below it, and beams near that column. So if I know the rigid stiffness of all the members, I can calculate two factors known as beta 1 and beta 2, like the equation given like this. Beta 1 is for the top joint, beta 2 is for the lower joint, by the ratio of stiffness of column to the beam along that joint. And with this ratio of beta 1 and beta 2 and the tables given in IS 456, we can calculate the value of K. So this is against when there is which is fixed against side sway. So how we can calculate the value of K using this beta 1? If I get zero point 0.5 and beta 2 I am also getting zero point 0.5, then my K value is something like this. And for other conditions, like this was for columns braced against side sway. If my columns are not braced against side sway, my K value is greater than 1. So what is that value? We can calculate using this graph by calculating beta 1 and beta 2 and then calculating the value of K. So using this, we can calculate the L effective. Okay. So by determining suitable value of beta 1, beta 2, we can calculate the L effective. Now for beam, you need to remember the stiffness of column directly we write as I by L. But for beam, if it is a braced frame, we take the stiffness of beam as I by 12, and for unbraced frame, it is taken as 3/4 times I by L by 2. Okay, so that these are some basic things that you need to remember while we are doing the calculation. Okay, so we will see one numerical on how the slender column is designed and everything. But for now, we'll stop here so that you can go back and clarify the short column designs and just look once again into this concept of how L effective is calculated. In the next class, we'll start with one numerical to just calculate L effective for one such cases, for one of these cases, and then we'll see the design of slender column. Okay. So just to conclude the week, we started our discussion on design of a centrically loaded column where we understood PM curve interaction and saw how reinforcement detailing is done. Then we talked about biaxially loaded column in which we saw how PM curve is used to calculate maximum moment and how design is done as per IS 456. Then we understood both of the above point by solving numerical for each, and finally we looked into slender columns, how axial loading cause buckling, and how additional moment due to slenderness is calculated. Okay, so I hope the week discussion is clear to everyone. Any doubts? It is very difficult to like design a column without using those interaction curves, because how we design basically by checking the neutral axis, and above neutral axis we see compression, below neutral axis we see tension and everything. Now in this case that is very difficult to understand or very difficult to plot. Okay, so that's why we use the assistance of SP16. And even IS 456 says like that. When you know moment and load, refer the SP16 charts that they are provided. That are provided only so that it is easy for you to do the calculation. Okay, so like without SP16, it is like very difficult to solve them because you won't be able to clearly find the neutral axis where it is. Any other doubt? Else we will close the session. Okay, so if there are no doubts, I will end the session now. Thank you.